speaking. So, probably the first thing I wanted to mention is which I believe is the 30th. We have test one. So, what do I want to say now? So, set up the formats on the files. So usually I like to have the class review using past finals that the math department wrote, but we recently changed our syllabus for Calc 1, and so we don't have that many finals that go with the new syllabus, so they removed all the finals, so now I'm just scrounging for problems to actually give you guys to practice. I think chances are what I'll just end up doing is maybe just write a couple mock tests instead, and just say, hey, just take these as tests, practice these problems, but yeah. So I was trying to find some old finals to get some questions from, but that's becoming a little harder because they took them down. So yeah, I'll tell you, so it covers everything we did. And it will cover today, including today, which is October 23rd. So it will have, there will be a bonus section as well, just like on the quizzes. I put bonuses on tests. In the bonus section, it will include related rates, which I plan on talking about on Monday. So if you've studied everything and you're really solid and you want some extra points, you can pay attention on Monday and try to get a bonus from on that. And some later topics. So I always like to put the bonus on the topic I'm about to teach. So whatever I would teach after related rates, which you can see in the syllabus, is probably what I'll put another problem on. So yeah, you'll know by far more information about what the test will actually look like. I'm thinking it's going to be between an hour and 15 to an hour and a half long. I'm thinking an hour and 15 minutes, like what I have envisioned in my head. But yeah, I will tell you guys exactly how to review. In terms of the topics, it's everything up to today, with a bonus on what I will be doing on Monday, maybe some other stuff. It will be, you have to write out all your work. It's not going to be like quizzes where I'm checking the answers. You have to show your work, and so you have to make sure you know how to write things down, which pretty much write things, solve problems like how I solve them on the board, and everything should be fine. In the meantime, there's a lot of things you can do until that the full review is up. What I would suggest that you do is you summarize. Your notes. You want to make it more efficient for you to study and start organizing the information in your head. A lot of times in class, I will derive a formula and then box it, then derive another formula and then box it. So the formulas are all spread out all over your textbook. Probably not a very efficient way to have them. Go through, write all the formulas down on one page. All right, so you're going to, so this will involve create a study sheet. I'm going to call it a cheat sheet. A study sheet with the following. So what should you be copying down from your notes? You don't have to copy everything, but those things you want to pay attention to. Formulas, rules. You want to pay attention to major definitions and terms. Do you want to pay attention to strategies? So, let's say you're going through limits. There will be a bunch of formulas that will apply. For example, the special trig limits would be some formulas that you write down. The limit as x approaches 0, sine x over x is 1. Limit as x approaches 0, tan x over x is 1, etc. There'll be a list of formulas and rules that go along with limits. You write down, a limit is just whatever the y value is approaching. If there is a contradiction in terms of which side I'm coming from, I get different y values, that's not going to work. So you'd write things down like that. You'd also write down the strategy that I gave you for limits. So if I'm faced with a random limit, what do I do? Step 1, try to plug in. Step 2, try to simplify if I can plug in. Step 3, apply a special technique. We did several special techniques. Step 4, look at the graph. Step 5, look at the table. You need to write all that down on a study sheet, right? So on one page, you'll see everything about limits. Here's what a limit is. Here are some formulas that apply. Here are the strategies. That's what you're going to start summarizing all that in your head, so you know what you're going to be doing. Right? So you don't want to be on the test kind of, wait, what should I do again? What did Jhevon do in class? I'm trying to remember. You don't want to be in that position, right? Because that's going to mess you up in more ways than one. It's going to mess with your psychology. It's going to cause anxiety when you don't know that. If you create a sheet with all these things, know it very well, you'll go into the exam, you'll feel very prepared. Once you see something, you'll immediately be able to start writing because you'll know what step 1 is for that thing. So I would start going through your notes and grouping everything because, you know, sometimes when I'm teaching, I derive all sorts of stuff that you don't even need to know, the derivation and things like that. But yeah, it's good for a class setting, I think, but probably not very efficient for studying. So I would actually take this time to rewrite some things. You're not going to be allowed to bring a study sheet into the exam, so everything you do on the exam you have to know in your head. So this is another opportunity for you to memorize everything you need. So, you know, the definition of the derivative should be in here on this page, all that stuff. All the formulas, everything I've ever written in a box should be on a separate page somewhere. As well as anytime I tell you a strategy. Here's step 1 for approaching this kind of problem. Write all those down. So that should take you a day, maybe a day and a half, and by tomorrow you should be able to actually start the actual studying process. But you definitely want to do that before you start studying, right? So that will kind of tell you how you should be studying, and so you don't practice doing problems when you don't really know what the strategy you should approach, then you get lost, then you kind of look something up. It confuses things in your head that way. So don't just jump into examples, really summarize everything, make sure you understand, okay, this is how this thing works. Then do examples. Then take a mock test. Okay? Because otherwise you risk getting confused. So that's probably what I would be doing in the meantime. But yeah, by tonight I should have some problems up for you to do. As well as, I'll also probably state specifically the things that I expect you to know. So make sure you know how to compute derivative using the limit definition. Make sure you know how to find a tangent line. I'll put a list of things that I expect you to know how to do the test as well. Okay, so that being said, let us begin. I think we had some examples to finish up. We didn't finish up even all the examples from someone to. So, next Wednesday, don't be late. Make sure you're early for that class. This is 3 times you need to be early for test 1, test 2, and the final. So, we're looking at something called implicit differentiation. This was how we can find the derivative of a function when that function is mixed up with the independent variable and we can't really solve for the function. The trick was to use the chain rule, and pretty much if you have some expression with x and y's and you want to find the derivative with respect to x, then you go through, you apply all the derivative rules, they still apply, you apply the product rule, the quotient rule, the chain rule, whatever. You see something with x, just differentiate it according to the rules. If you see something with y, differentiate according to the rules and then multiply by a y prime. Basically what implicit differentiation is. It's a little bit more complicated than that when we throw in more variables, because we're going to look at situations where we have more than 2 variables, and it just depends on who you're differentiating with respect to. Just make sure you apply the chain rule, multiply by the derivative of the inside. That being said, we had some examples. I believe I did one from the quiz, and then I did 2 examples, and then we had the van der Waals equation left over. So P plus 5 over V squared. So I'm not sure if any of you are taking chemistry right now, but eventually you'll see that equation. P represents pressure and volume, and V represents volume here for a specific gas. I want us to find how fast is the volume changing with respect to the pressure. Every time I increase the pressure by 1 unit, how would the volume respond? How quickly would it respond? And I think was that the last example? So, let's start this over here. Should I start over there? I don't know. Let's just start. Okay, go. Tell me what to do. See what we remember. Yeah?
First I distributed, and then the derivative of both sides.
Okay. You distribute it first?
Yeah.
I mean, that's fine, I guess. You could also just directly do the product rule, but let's say you wanted to distribute. So, take the P, multiply everybody here. Take the 5V to the minus 2, multiply everybody there. That's 5 over V. Minus, what's 5 times 0.3? That 0.15? 9.7. So here, just distributed P times V, PV, P times this. We have that. This times that, we have that, this times that, we have that, and then we have 9.7. Now let's go through and differentiate. How do I differentiate the first term?
It'll be 1, the derivative is 1 times B plus the derivative of B times B.
What's the derivative
of B prime.
Now here, what you want to notice is that the P is the guy in the bottom of the derivative notation. That tells you that P is the independent variable. It's like the X that we were used to. And in this case, the V is like the Y. So pretty much what happens is whenever I'm differentiating a P, I don't really have to do anything. I just apply the derivative rules, pretend it's like an X. However, when I'm differentiating the V, I want to think of the V as a function of P. The guy on top you can think of as a function of the guy at the bottom. So there's some inside function inside this V that I'm not exactly sure what it is, but whatever it is, to differentiate it, it's going to give me V prime. Here I would have minus 0.03 by differentiating the P plus
negative 5 times V prime over V squared.
negative 5 5 over v squared, because the derivative of 1 over v would be 1 over v squared, but then we have to multiply by v prime, because it's the dependent variable. Then,
I wrote it.
the name of this as v to the minus 2,
Yeah.
and do the power rule, right? Don't do the quotient rule at this point. So that's going to be plus 2 times 0.1 over v2. And all of that is going to be equal to 0, which is the derivative of the 9.7. Now what do we want to do? Times v prime. Now we want to solve for the v prime. What are we going to do?
Group the b primes and then factor it out.
So who's attached to the v prime? Well, there's the p. There is the minus 5 over v squared. And there's that now 0.3
Yeah, 0.3 over.
plus 0.3 over v2. Those are all the guys with the v primes in it. I'm going to move everyone without a v prime to the other side, so that's going to be the minus 0.03. It's going to come over and be positive 0.03, and the v is going to come over here and be minus v. So here, I have v prime. That's just another way of saying dv dp is going to be equal to 0.03 minus v over q minus 5v squared plus 3 over v cubed. Which, we can make that look a little bit nicer by multiplying and dividing by v cubed. 0.03 v cubed minus v to the 4th over pv cubed minus 5v plus 0.3. And that is how the volume is changing with respect to the pressure. Questions? Now, I want to show you a technique which uses implicit differentiation. We're going to have several of them. We're going to want to introduce something called logarithmic differentiation. Here's the motivation. How would we differentiate x raised to the x power? Now, some people might think bringing the x down and subtracting 1 is going to be what you should do. This is not what you should do. I want you to note very carefully, power rule does not apply. What does the power rule say? What is the power rule? Huh? What? Yeah. d dx
of the x to the power of n
x to the power of n.
equals n times x n times
Right. Now tell me about what is n? N, you should know, needs to be a constant. Okay, now, looking at that, it looks like x to a power. Is the power a constant? The answer is no. Do not apply the power rule. It does not apply. This is another thing that you should be doing with your study sheet. Make sure that when you write down a formula, you actually understand the formula, understand what the individual pieces in the formula are. Because just because something kind of looks like something doesn't mean it is the thing. Power rule will only apply if the power is a constant. Also, there's another rule where we had something with a power. It tells us how to differentiate a to the x. What is the derivative of a to the x? Yeah? A to the x, ln what? Ln a. And in this situation, what is a? Yes, well, what is it? It's a constant. What kind of constant? Yeah? Positive constant. It's a constant that's greater than 0. Right? You need to know that. Okay. Now, that also does not apply. To be able to use the power rule, the power needs to be a constant. Doesn't apply. To be able to use this rule, the base needs to be a constant. Doesn't apply. I have a variable both in the base and the power. This is a kind of function that we don't have a rule for. Not yet. So, well, for one, the first thing you need to realize is that you need to recognize that you don't have a rule for something when you're looking at something that you don't have a rule for. Doing a study sheet is going to help in that endeavor. A lot of times students just go and they apply all sorts of rules to something because it kind of reminds them of a rule. Not good enough. You need to know the rules exactly, which is why you need to write it on a study sheet, which is why I always ask you about them on quizzes, because one little thing messes up and the rule doesn't apply anymore. So now, how can we do it? Here's an approach. How are we going to figure this out? Similar to how we actually derived the power rule, actually. Set y equals to this function. And of course, you know, we want y prime. Now what we're going to be doing is, since the power is an issue because the power is a variable, if it was a constant, we would be fine. We want to get rid of the power. So, I was going to ask you what you could do to get rid of a power, but I kind of gave it away with the title, right? Whenever a power is giving you an issue, a logarithm is what you should be thinking, right? Just like how, you know, if you want to solve an equation that's nonlinear, bring everything to one side, say equal to 0. It kind of triggers this strategy in your head. That's a general principle. If a power is giving you an issue, a logarithm is what you want to do. Try to get a logarithm in there somewhere. And so what you can do is you can log both sides. We'll use the natural logarithm because this is calculus. And what that allows us to do is it allows us to take this power and move it down in front as a multiple. Now I don't have something with a power anymore. Now what I'm going to do is start differentiating. Now I want y prime, but I have a function where I don't know what y is. Well, I know what y is. But in this form, I haven't solved for y. This here, y is implicitly defined here. Which means implicit differentiation applies. So what I'm going to do is differentiate implicitly. Derivative of ln y? Y prime over y. So it's 1 over y times y prime because of the chain rule. Derivative of x ln x. ln x plus 1. How do we get that?
It's ln x plus.
Sorry, 1 times ln x plus x times 1 over x. So I applied the product rule. The x's would cancel in this case, so that gives me ln x plus 1. The plus 1 is not inside the ln, right? So if I wanted the plus 1 inside the ln, I would put parentheses here, just be aware. Okay, so that's what I have. Now, just like before, I want to solve for the y prime. So I'm just going to isolate y prime in the formula. That's going to move the y, multiply both sides by y. And we're going to have that. Now what I can do is replace the y with the expression that I knew what it was before, right? It's actually exactly what we did in the proof of the power rule. That is our answer. That's the derivative. The derivative of x to the x is x to the x times ln x plus 1. In fact, on the quiz, we had a similar thing. Let's just run through that example very quick. We had a couple versions. In one of them, I asked for the derivative of sine of x to the x, I think. Maybe the other one asked about cosine, but that was one of the bonus problems. This has the same kind of issue. So, and I think at this point let's do that and then I'll talk about I've asked it on a couple quizzes at this point, but I want to make sure that it's clear for the test. Yeah, so here we have sine raised to a power. The power is a variable though. So how do I deal with that? One thing you can do is you can set y equals to the sine of x raised to the x. You can take the ln of y equals the ln of sine of x. And of course you're going to move the x down. Then you can differentiate both sides. Y prime over y is going to be equal to the product rule. Differentiate the x, leave the ln alone. Plus, leave the x, differentiate ln of sine x. What's the derivative of ln of sine x? Right, it's cosine of x over sine x, or cotangent of x. And so now, but y prime equals y times ln of sine x plus x cotangent x. Or in other words, that's equal to sine of x raised to the x. And that's the derivative. That's the slope to the graph of sine x to the x. So this process that I just went through, this is called log differentiation, logarithmic differentiation. Why? Because I use a log. Here's a non-example. I just want to make sure that we actually know. I put on a couple quizzes, but I don't know. I don't recall if I did it in class. So this is not an example for this topic, but I just thought of it when I did that. If you wanted to differentiate sine squared x, I think a lot of people got that wrong several times. So just want to make sure. How do you actually do that? Yeah.
So you could write it as sine x squared and do power.
Right, so one thing you need to remember is that when you see this, what it really means is the entire sine is squared. Right? Now, it's very different. Versus if I have the derivative of sine x squared. Right? That means the sine and the angle is squared, as opposed to the sine and everything is squared. Anyway, what would we do here? How do we differentiate that? Chain rule. There's an inside function and an outer function. The square is the outer function. Differentiate the outside, leave the inside alone, multiply by the derivative of the inside, which by now, hopefully, you know is cosine. You get 2 sine x cosine x, which there is a trig identity for that, which is sine 2x. This is for the double M form for sine x. So cosine squared x is going to be dealt with very similarly. You'll actually get the negative of cosine 2x. So yeah, make sure you understand that. So if you see like a sine cubed or anything like that, you look at it like this, like the power is on the outside. If you have the power it's just off to the side like that, what that means is the angle that's taking the square. If you put the square over here, it's the entire sine function taking the square. So be aware of that. In this case, you would also do the chain rule, but this time the sine is the outer function and the x squared is the inner function. That's going to be cosine of x squared times the derivative of the inside, which is 2x. So that would be 2x cosine x squared. So those are different. I just wanted to make sure. I was looking over the quizzes I saw. More people making a mistake at a point where I don't want them to be making that mistake. First time it shows up, fine, but I put this on a couple quizzes at this point, and people are still messing it up. So that's just a small detour there. Let's now to find the derivative of x to the x and the derivative of sine x to the x, we used what's called logarithmic differentiation or log differentiation for sure. Here are the steps in log differentiation. To compute the derivative of y equals x, you are going to you're going to log both sides. We're going to simplify. The point of doing this is to simplify using the logarithms. I will talk about when we want to do the log differentiation a little bit. 3, they're going to differentiate implicitly. Or you're going to solve for y prime. These are the steps in log differentiation. When would you want to try this? Two main times. 1, if a power is giving you trouble. If you have a crazy power and the base is a constant, it doesn't actually matter that much because your ddx of a to the u formula will actually take effect. But let's say your base is also complicated and on top of that you have a complicated power, log differentiation is probably what you want to think. So you see like x is in a power or something like that. Chances are you want log differentiation if the base is not constant. So yeah, these were prime candidates. X in the power, x in the power. It's kind of weird to do with x in the power. We didn't have a rule for it, so we can use logs to actually bring powers down. But as you might recall, logs have a lot of other nice properties as well. They turn products into sums. They turn subtractions. They turn divisions into subtractions, etc. So you can use them other times, not just to deal with complicated powers, but whenever you're faced with something that is it's just annoying, kind of. What do I mean by highly annoying? Let me give you an example. Say for some crazy reason, I was in the mood to ask you to differentiate this on a test. Find the derivative of the square root of x squared plus 1 e to the x squared times sin x all over cube root of x plus 2 times, I don't know. Now I'm getting kind of ridiculous, but you can kind of see where I'm going with this. Right? You have something like that. Now technically, you could actually do that going through the rules. What's the quotient rule? So it's the bottom times the derivative of the top. In the top, there's like a triple product rule with a chain rule. Minus the top times the derivative of the bottom. That's a product rule with a chain rule all over the bottom square. You're going to have this entire huge mess, and it's going to be really annoying to start to clean that up and simplify. This is highly annoying, right? So there's just a lot of stuff going on. You have things raised to all sorts of powers, like 1/2 power here, 1/3 power there, products and divisions all over the place. The thing is, logarithms actually deal with those very nicely. They can split up products and they can split up divisions using addition and subtraction respectively. So what you could do here is just set this equal to y, this whole thing, right here. And then, if I take the log of both sides, what is the right side going to break up into? Well, it's going to be the log of this plus the log of that plus the log of that minus the log of this minus the log of that. Now the log of this, I can reach that to the 1/2 power and bring the 1/2 down. So I'm going to end up with 1/2 ln of x squared plus 1 plus ln of e to the x squared, which is actually going to cancel and give me x squared, plus ln of sin x minus 1/3 ln of x plus 2 minus ln x. Right? Now, yes, that looks like a long string of things, admittedly. However, if you look at each individual term, they're ridiculously easy to differentiate. So, what I'm going to do is I'm going to start differentiating both sides. Y prime over y. Derivative of this. Two x over x squared plus 1, and the 2 is going to cancel with this, so it's just x over x squared plus 1. Derivative of the x squared is 2x. That's literally the very first time we learned to differentiate it, we figured that guy out. This guy is going to be cosine over sine. This guy is going to be 1 over x plus 2. So that's minus 1 over 3x plus 2. And then this guy is going to be 1 over ln x times the derivative of ln x, which is 1 over x. So this is going to be 1 over x ln x. Yeah, we had a few terms to differentiate, but each of those took a second, 2 seconds to actually do. It's not really a big deal. Versus doing this with the directly by the quotient rule and the product rule, forget about it. We'd be here forever. We'd be here past the end of class. Then all we have to do now is solve for y prime. And y prime is going to be now sometimes if the function is completely ridiculous, I'll allow you to leave y in the answer, but for illustrative purposes, let's just actually put this in. And then you times all of them. Minus 1 over x ln x. And that would be your answer. Yes, it's a huge answer, but you can imagine, had we done the quotient rule directly, how monstrous that would have been. The quotient rule will actually have given you, once you factor this out, the combined form of all these fractions, and you just have like one big meh, right? Which a lot of things could go wrong with one big meh on a test. You don't want to have that, right? So log differentiation comes in handy whenever you have variables in the power. Also comes in handy whenever you just have something that directly applying the product rule, the quotient rule is going to be it's going to be a mess. So what you can do is you can split up the products and the quotients using logs. So you just ln both sides and remember to multiply by the original at the end, and that's log differentiation. Now, there is a variation on how we can actually write this down, which a lot of times is very convenient, because sometimes it's inconvenient to go separately and set y equal to that thing I was looking at and then do this. So there's actually a way to do log differentiation on the spot without setting up some other variable to measure things in terms of. So let's look at that. Variation of log differentiation. Recall. Now, of course, this is going to work for positive x's, but via a log rule, we have that this is true. If you have some quantity, this guy, we can write it as long as it's positive, or we can force it to be positive in some situation. We can actually rewrite that with exponentials and logarithms. Remember that if the base of the exponential and the base of the log are the same, they cancel each other. So in fact, if you give me any expression, once that expression will work inside a logarithm, I can automatically write that expression as e to the ln of that expression. Right? That's true by a log rule, right? It was rule 8 or 9, one of those. Way back when we were doing logarithms, like lecture 2. It's been a long time ago. But that was actually a rule. So what that allows me to do, you might notice, is that I have some expression, but I can rewrite it in a way that I get the log of that expression right on the spot. So, how can I apply this to my advantage? So, let's redo the example of d dx of x dx. What I could have done here is write this as d dx of e to the ln of x dx. So I don't have to go separately, set y equals this and then log both sides and blah, blah, blah. No, just rewrite it right there on the spot inside an exponential. This is going to be the derivative of e to the x ln x. Now what's the derivative of e to the something? It's the derivative of the power times the original function. Right? Because we know d dx of e to the u is u prime e to the u. So once I want to differentiate the exponential to something, I'm just going to differentiate the power and put it down here. Now in the power, that's the product rule. I'm going to differentiate the x, leave the ln, plus leave the x, differentiate the ln. And that's the answer, that's the derivative. I can of course clean this up a little bit. That's ln of x plus 1 when these guys simplify. And this one, the e to that guy, was just the original guy. So I can just write it back. And that's your answer right there. So you can do it on the spot. That's convenient because sometimes you have a sum of things where you don't really need log differentiation for all of them. Mixture is not the right word, but whatever. Mixture of techniques is needed. One of which is log differentiation. So, for example, I could ask you differentiate sine x. Let's make it cosine x to this. Switch things up a little bit. Plus x squared. Yeah. Now you see something like that. You want to differentiate both of these. Now of course the x squared part is something you know how to deal with. Oh, it's fine. You don't need anything special to deal with that guy. That's just a regular rule. But you're adding it to that. So we know that the derivative of this is going to be the derivative of this plus the derivative of that. Now, the first way we did it, what you should do is you can't just ln the whole thing, do log differentiation, right? Because then you put the plus inside of the ln and you can't distribute it, right? Logs do not distribute across pluses. So, what you would have done is you would have to go separately. Okay, come over here, set y equals cosine x to the x, blah, 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 work it out, and then come back and plug it into the derivative. Or, I can just rewrite it right on the spot. Right, this has e to the x ln of cosine plus x squared right there. And I don't need to separate anything. And at this point, that's just the derivative of the power times the original function, which is going to be cosine of x to the x. The derivative of the power is going to be ln of cosine x minus tangent x, and then plus 2x. That's going to be your answer. So writing it as e to the ln of, writing something as e to the ln of something on the spot makes it more convenient to do log differentiation when you have other things going on around that you don't want to use the log and affect those things. Because those things are fine. I just need the log on this one guy over here, so you can just rewrite that guy in the spot. Instead of having to think separate, that's a bunch of separate problems. So that's nice that way. that's log differentiation in a nutshell, and I'm thinking. As opposed to doing more examples, I think I'll go into a different topic where we use log differentiation to help us out anyway. So here is another nice thing. Where this sort of thing is going to actually help us out a lot. Let's look at another special technique. For limits. Yes! I know you guys miss limits. Let's take it back a little bit. There is something called L'Hopital's rule. I don't think L'Hopital is the guy that came up with it. Some people pronounce it hospital. I think L'Hopital is actually, I think it's actually French for hospital. I don't know if anyone speaks French who can confirm that. But yeah, so there are times when you can actually do limits using something called L'Hopital, if you want to be French. Okay. So here's what the rule says. Suppose you have the limit as x is approaching something of a division of functions. And suppose this limit approaches one of the following two forms. It will approach 0 divided by 0, right? You're not literally divided by 0, the limit is going towards that way. So both the top and both the numerator and denominator, as you take the limit as x approaches 8, they're both going to 0. They're both getting smaller. Or they're both becoming infinity. Infinity over infinity can be plus or minus here. Okay. So you have a limit that's a ratio. If you realize that the top is going to 0 and the bottom is going to 0 at the same time, or the top is going to infinity and the bottom is going to infinity at the same time, then L'Hopital's rule takes effect. And the following will hold. That limit that you were considering originally will be the same as the following limit. Take the derivatives of each of the functions and find the limit of that. Now, be aware, I'm not applying the quotient rule. I'm literally taking the derivative of the top and the derivative of the bottom at the same time. Those two limits will actually be the same. They'll always give you the same answer. And this may be repeated as necessary. Sometimes you can do this repeatedly, as long as 0 over 0 or infinity over infinity is obtained. This is called L'Hopital's rule. It's now a new limit technique. You're looking at a limit, it might look crazy, whatever, it's two functions dividing each other. The top and the bottom is going to 0 at the same time. Or the top and the bottom is going to infinity at the same time. Maybe one is going to positive, the other is going to negative. The sign is not going to matter. But the top and the bottom are becoming infinitely large. Then the limit that you care about will be equal to the limit where you just differentiate the top and bottom separately. And if that ends up being a limit that behaves like this, you could do it again, differentiate the top and bottom again. And do it again, do it again. Eventually, the idea is that you'll slip out of this case and get into something that's more doable. Now, there are examples out there where you can do L'Hopital's rule forever and it's not going to help you, but a lot of times it is helpful. Now, let me just mention something else here, because it's not always that you'll have something in this form specifically you want to apply L'Hopital's rule. Sometimes you'll have other forms that you can kind of maneuver into these forms and use L'Hopital's rule. These forms are called indeterminate forms. Let's talk about those. So there's a kind of thing called an indeterminate form, and it refers to limit forms. So when you're taking a limit and you're just looking at how things are behaving, and you want to see how what each part of it is going towards in the limit, you can get something called an indeterminate form. It refers to limit forms of the following type. So you're taking a limit, right? But if you just look at the limit without really simplifying much, you will start to see that it will approach one of these forms. There are about 7 of them. I feel like every time I write this list, I forget one of them. I mean, I recognize when it's on paper, but to actually remember the list off the top of my head. Okay, 1 is 0 over 0. The other is infinity over infinity. I'll talk about why they're indeterminate in a bit. Another one is 0 times infinity. Another one is 1 to the infinity. Another one is 0 to the 0. Another one is infinity minus infinity. And there's another one. This also. It's obvious when it's there, but then I always forget it when I'm writing down the list. There are like 7 of them. Okay, 0 over 0. No, 0 to the infinity, we'll know what it is. I think there's one more. I forgot it. They'll probably come to me. But these are indeterminate, meaning cannot be determined, at least not at face value. So there are some conflicting ideas. So for example, everyone would tend to think, well, if the base is 1, then whatever power you're raising it to, it should be 1. But it turns out there are examples when if the power goes to infinity, 1 to the infinity is not going to be 1. By the way, the limit that defines E falls in this category, right? So remember we had that the limit as x approaches infinity, n approaches infinity of 1 plus 1 over n to the n was actually E. But look at what is actually happening in that limit. If you look at the base here is approaching 1. As n goes to infinity, 1 over n goes to 0. The inside is going to 1. As n goes to infinity, the power is going to infinity. So this looks like 1 to the infinity, right? At face value, that's what it looks like. I'm looking at that, looks like 1 to infinity. So now you're thinking, well, the base is 1. It should be 1, right? It's not. It's 2.7, right? So it's not going to be something you can look at face value because it has competing ideas. So on the one hand, if the base is 0, the thing should be 0. But on the other hand, if the power is 0, it It should be 1, right? X to the 0 is 1, isn't it? Right? So here there's a competing idea. You're not sure, is the base winning or is the power winning, right? Here, 0 times infinity. 0 times anything should be 0, but infinity times anything should be infinity, right? Who's going to win, right? Or infinity minus infinity. Well, is that 0? Not necessarily. You can have infinity of different sizes, right? So this could be infinity, it could be 0, it could also be 7, right? It could be whatever. This could be whatever. Infinity divided by infinity could also be whatever. Think of something like, I mean, it's a silly example, but just to illustrate, 3x divided by x, that's 3. But if you look individually, that's infinity. And that's going off to infinity. That's an infinity or infinity. But I could have changed that 3 to a 5. Now the answer is 5. Now the answer is pi. Right? Sometimes you have infinity over infinity, and it can be anything. Isn't anything divided by itself 1? Not necessarily. Not when it's infinity. Right? So it's when you have all these competing ideas where it's like, on one hand, the answer is obvious, but on the other hand, it's obvious in a totally, completely different way. And these two ways don't mesh well together. So we say it's indeterminate. I can't determine what this is just by looking at it. And it turns out that L'Hopital's rule helps us with 2 of these forms. It's very important that you know L'Hopital's rule only applies to these 2. They're all indeterminate forms, but the rule that I mentioned before, L'Hopital's rule, only applies to the 0 over 0 or the infinity over infinity form. It does not apply to any of the other forms. However, the nice thing is, using logarithms in very convenient ways, or sometimes using factoring or simplification, I can modify one of these other forms to look like that. So, for example, in this case, the 1 to the infinity, what I could have done was if I ln this, I can move the power down. I would get n times ln of that thing. I can take that n, move it to the bottom, write it as 1 over n, and suddenly now I get a fraction. And you'll notice that the fraction itself will actually approach 0 over 0 in that case. Right? So there are ways that we can modify the other forms to actually get to what we want. But we're going to do a few examples soon, but it's actually kind of bothering me that I don't remember the other one.
Oh, I looked it up and it was infinity to the power of 0.
Infinity to the 0. That's the one. That's the one. It's one of those things when you see it, it's going to be obvious, but just remember the list off the top of your head. That's another one. Because that's one where, like, well, if the base is infinity, shouldn't the answer be infinity? But at the same time, if the power is 0, shouldn't the answer be 1? Who knows what the hell that is? We don't know. Okay. Well, at least we don't know without some calculations. Without some more sophisticated calculations. So that's something that you might, well, I'm definitely going to put at least one problem like this on the test. A limit that behaves like one of these weird ways. And you're going to have to know how to do it. So let's look at some examples where we're going to be dealing with these indeterminate forms, and we are going to actually, either we're going to figure out a way to get L'Hopital's rule to apply to the form, or we are going to simplify it some other way where we won't even need L'Hopital's rule. We can do something else. But I'm not going to tell you which is which. We are going to figure it out. White. So here are the examples we're going to go through. Now, the first few, we actually would know what the answer is. They're easier, but I want you to actually think of them in terms of L'Hopital's rule now. This, you should know that that's 1, just saying. But if you look at it individually, notice that this approaches 0 over 0. So let's say you're anxious on the test next Wednesday and hell freezes over and you forget that that's 1. If you also remember L'Hopital's rule, you now have another way to figure out that that's 1. We're going to actually do that. So you should also know that's E. I'm going to show you specifically what I was talking about when I was rambling over there. Get through a few of these. So we have the indeterminate forms at face value. It does make sense that what value they would be because they're obviously one thing or obviously another thing, and it turns out in reality they might be neither of those things. L'Hopital's rule helps us with two of these forms, the 0 over 0 or the infinity over infinity. Because if 0 is in the numerator, it's supposed to be 0. But if 0 is in the denominator, that's impossible. How do we put these together? Let's look at A. One thing you can notice is that this would approach the form as x approaches 0, sine would approach 0, right? Sine of 0 is 0. And as x approaches 0, x would approach 0. So you have a 0 over 0 form here. Now you can say, oh, I can apply L'Hopital's. Here's how you're going to show that you're thinking L'Hopital's, which I would expect you to indicate. Right? Equal sign, limit, x approaches 0, of the derivative of this over the derivative of that. And then on the equal sign, write L apostrophe H. That indicates to me, oh, you got from this line to that line by applying L'Hopital's rule. Boom, that's what you're going to get. Now that, of course, is just the limit of cosine of x as x approaches 0, which is going to be what? That's now obvious, right? Cosine of 0. Then you follow step 1 in the limit strategy. Just plug in 0. That is 1. By the way, you should know this by heart. Just want to make sure. I don't want to see anybody on the test like using L'Hopital's rule to figure this guy out. Okay, but I'm just illustrating the method with you with something that's familiar, so you don't have to pay attention to too many things at once. Okay. So. Worst case scenario, you forget what the limit as x equals 0 sine x over x is. You can use L'Hopital's rule because it approaches the indeterminate form 0 over 0. Here's also one that we would know how to do with. What's the answer? Infinity would be the answer, right? You know that because of strategy 5 when we dealt with limits. knowing how the different functions relate to each other. Exponentials are way bigger than polynomials as we're going on to infinity. So the numerator is going to overwhelm the denominator. I know the answer is going to be infinity. But let's pretend we don't know. What does the top approach? As x approaches infinity, e to the x will approach infinity, because the graph looks like this. And of course, as x approaches infinity, x approaches, well, infinity. So this is an infinity over infinity. So what I can do is I can apply L'Hopital's rule. This is going to be the same as the limit of the derivative of the top divided by the derivative of the bottom. That's just the limit as x approaches infinity of e to the x, which that is now clearly infinity. Again, you should know this. Save L'Hopital's rule for when you really need it, because the first A, B, and C, they're all they should be obvious, based on strategy 5 that I told you with limits. Yeah, so that means. Now this one, again, strategy 5 reminds us that logs are much smaller than polynomials. So as we're going off to infinity, top is going to be much small, very, very small compared to the bottom. So the denominator is going to overwhelm the top. That's supposed to approach 0. Let's say I want to actually show that with way more computation than is necessary. Again, I would look at this. As x approaches infinity, ln x approaches infinity, because ln grows like that. It approaches infinity, but very slowly, at least compared to a polynomial. And as x approaches infinity, x approaches infinity. There's the infinity over infinity again. So now I can actually apply L'Hopital's rule. I'm going to differentiate the top and differentiate the bottom. So that's just the limit as x approaches infinity of 1 over x, and by now we should all know that that's 0. So, first three not surprising, I'm just kind of illustrating the method. D is kind of interesting though. Limit as x approaches 0 from the right, because the limit in general here actually does not exist, but from the right-hand limit actually does exist. Now you look at that. What does this approach? What does the form look like? Huh? What? What do you mean 0? Huh? Not the answer, the form. What does this look like?
0 to the 0 power.
0 to the 0, right? X is approaching 0, so the base is going to 0, and the numerator is going to 0. This looks like a 0 to the 0. So, what we can do is apply L'Hopital, right?
No.
No. Right, you try to jump into L'Hopital's at this point and throw the chalk at it. L'Hopital's rule does not apply to the 0 to the 0 form. It applies to 0 divided by 0 or infinity divided by infinity. So L'Hopital's rule cannot be applied as this thing is written here. What do we do? Yeah? Yeah?
Oh, the log. Sorry, I zoned out. The natural log.
You're like answering the question,
Yeah.
and so no, it's too early. Yeah, I get it. 8 a.m. math class, it's just, I don't know, it should be illegal, I think.
So
I don't make the
do we take the natural log?
Well, you can't just take a natural log, no. Because that will change the value, right? What I could do is I could rewrite that though on the spot.
E to the
By writing e to the ln of x to the x, which allows me to bring the x down. So that's just I can do that. I could log both sides, but I'll need another variable to keep track of this. I'll probably do it the other way just to show you. But I could do that. The trick that we just learned to get this thing now can come down. So this is the limit as x approaches 0 of e to the x ln x. We also know a rule that limits actually pass through continuous functions. We looked at that before. So this actually becomes e to the limit of x ln x. I had meant to write this one a little bit earlier, but by the time we do it next week, you'll probably forget about this. Hopefully not. You should be studying this weekend. So we have this. Now, what does the power approach? What is the form that this is approaching? 0 times? Right, negative infinity specifically. But that's 0 times infinity. That's still an indeterminate form. Is it one that I can use L'Hopital's rule though? No. So why do you do this in the first place? Well, we're not done. We can rewrite it more. Here is a very clever trick, how you can write a product as a division, which of course you know because it's algebra, but I could instead write this as ln of x divided by 1 over x, right? Because of the keep change flip, that's going to turn into x ln x. Now I can do this because my x is not actually 0. We're getting close to 0. So I can write 1 over x to represent x. Did you have a question?
Yeah, how did we know it was times infinity?
Oh, because the x is times, because you have the limit as x is going to 0 of x times ln x. You just look at it naively. What is this piece doing? 0. What is that piece doing? Infinity.
Oh, okay.
You literally just look at it as it presents itself. You look at it as face value, right? And the face value is an indeterminate form. But that wasn't a convenient form. So this isn't convenient for us, this isn't convenient for us. However, if I write it like this, what's going to happen? Well, as I approach 0 from the right, ln is going to go to negative infinity. As I approach 0 from the right, 1 over x goes to positive infinity, right? Because it's going to go this part is going to go to positive infinity. So I have the infinity over infinity now. So this means L'Hopital's rule would apply in the power. I can apply L'Hopital's rule. That original limit is going to be equal to the limit obtained if I differentiate the top, 1 over x, and differentiate the bottom separately, minus 1 over x squared. Now what? Can I find that limit? It still looks like infinity over infinity. However, we can get out of that loop. If you keep going, it's going to keep looking like that. But there's a way to get out of it. And that way is, of course, well, it's usually the way you get out of a calculus kerfuffle, algebra. So what you do first is just simplify. Every time you apply L'Hopital's rule and it seems like L'Hopital's rule presents itself again, just simplify. this fraction divided by that fraction, you flip the minus 1 over x squared and multiply it. This just becomes minus x. It simplifies to minus x. And now, that's not indeterminate. I know exactly what that is. As x approaches 0 of minus x, the answer is 0. So this is going to be e to the 0. So this limit is actually 1. So you're given something, has an indeterminate form. The power is kind of what makes things crazy. Get an ln in there some way. We can do it by this rewriting technique. We can then focus a little bit on the power. In that case, it was another indeterminate form. We can rewrite this into L'Hopital's rule form and then simplify and get to the answer. Another thing you could have done here, I'm doing the same problem, it's just a slightly different way to write it out. Personally, I prefer this way, but other people might not like having to do everything with the power. So if you're given that limit as this approaches 0, x to the x, what you could do is you could just set y equals that limit. You can log both sides. Limits pass through continuous functions, so I can move it outside the ln. We can only do that when the thing we're looking at is continuous. FYI. Now I can move this down, and so I would get ln of y is equal to the limit as x approaches 0 plus of x ln x. Now that approaches the indeterminate form in 0 times infinity, so at this point I would rewrite it remember, I'm keeping the ln(y) here the whole time. I'm just simplifying the right side. That's going to be the limit as x approaches 0 of ln x over 1 over x. This approaches infinity over infinity, so what I'm going to do is apply L'Hopital's rule. It's going to be 1 over x divided by minus 1 over x squared. That's going to be the limit as x approaches 0 of minus x. That's going to be 0. And so what I have is I have ln of y equals 0, and now you just solve for y by e-ing both sides. So you could get the answer that way as well. So whenever you want to get the log in there, you can set y equals to the thing that you want to put a log on and do it, or you can rewrite it in the spot as e to the ln of that thing. In either way, as long as that thing is positive, it's going to be nice. You can move limits outside, inside and outside of the ln, and simplify things that way. So this answer is actually two different flavors to actually do that. But we'll stop there. Try the other examples on your own. We'll pick up with those on Monday and related rates, and your test will be on Wednesday. So Monday there's no quiz, but you should be studying and make sure you actually go through the reviews that I'm going to post.